is the lesson on 6.4, solving trig equations using identities. So we did this one first, right here. 2 sine x equals 1. We divided by 2, and then we solved it out. The other one we've done so far is common factoring. So if we have a mix, like sine x, tan x, and sine x, we've always been able to take something out. So we take out a sine x, we're left with 2x plus 1. Then we set them both equal to 0 and solve them separately. The other ones we've dealt with were difference of squares. So we did it as a difference of squares, or we went sine squared x equals 1, square rooted, and when we took the square root, we made sure to take the plus or minus. So if you forgot to do difference of squares, it was fine, because you still got all 4 answers, plus or minus 1. And then you solved that. The last thing we looked at was trinomial factoring. So we had 2 sine squared x minus sine x minus 1. We replaced them with m's if we wanted to, factor it out by difference of squares, get your 2 answers. And then remember, you had to actually find out where these occurred. So we weren't done at this point. We'd have to find out where sine x equals negative a half, which would be in quadrant 3 and 4. And we'd have to find out where sine x equals 1 and sine x equals 1 where y equals 1. So it would be at x equals pi over 2. And then you'd have to solve where sine x equals negative a half, which is at the 30-degree reference angles in quadrant 3 and 4. So that would be 7 pi over 6 and 11 pi over 6. So we have to keep going, correct? Now, today's lesson is where it's not that nice. You can't maybe just take a sine x, a GCF out. You might have to replace it. So this is more the type that we're doing today. So you have cos 2x minus 2 sine x plus 3 equals 0. Now, what's easiest to replace out of that? Not the sine, because there's nothing to really replace sine with. But we can take the cos 2x and we can go to our formula sheet, and there's 3 of them. Now, there's 3 formulas we could choose. We could use the one that has sine squared and the minus cos squared one, but that wouldn't help us because then we'd have sine squared and cos squared, so it'd be a mess. We could use the cos squared one. But that wouldn't help us because then we'd have a cos squared, a sine x, and a 3. So the only cos 2x formula that's actually helpful to us is 1 minus 2 sine squared x, because then we have a sine squared x, a sine, and a number. So once we replace these, we could take that 1 and that 3, combine them, and we get a 4. And then we would have to factor by decomp. Or in this case, if you didn't want to take factor by decomp, you could take out a negative 2, and you'd have this left over. Then you could factor that normally. So you'd have your sine squared x plus sine x minus 2. And we're back to exactly the way we solved in the previous question. So we'd factor that, and we get sine x plus 2, sine x minus 1. We get sine x equals negative 2, and sine x equals 1. Well, sine x equals negative 2 nowhere, because your sine x graph goes as low as negative 1, but it doesn't go any lower. So if you drew your sine x graph into y1 and into your y2 you had negative 2, your graph would go like this, and then negative 2 would be down here. They would never cross. So this sine x equals negative 2 will get you no solution. But if it was cos, it would still get you no solution. But if it was tan, tan does cross at negative 2 because it goes on and on forever, YER as your domain, as your range. Your domain is the one that's restricted with tan. Now sine x equals 1, once again, when y equals 1, and y equals 1 at pi over 2, or 90, depending on what they ask us. Or we can be asked to give general form as well. Okay, so this is the type we're going to be looking at today more so than the other types that we've done before, quite a bit of. So these ones are our basic solving like we did before. We're going to skip those. So if you see, there's a whole bunch. You can practice these if you'd like, but we practice these a whole bunch at the beginning, or at the end of Trig 1 and at the beginning of Trig 2. So we're going to keep going until we get ones that are mixed up. So it says, solve each equation algebraically over the domain 0 is less than or equal to x is less than 2 pi. Verify your solution graphically. So we have sine 2x minus 1 equals cos 2x. This one's kind of a little bit more tricky, but what I do know is that sine 2x only has one formula I can switch out. So I'm going to do that one first. So 2 sine x cos x minus 1 equals cos 2x. Now, instead of putting cos 2x, I'm going to have to swap that out with one of the three formulas. And honestly, if I can get this -1 to go away, it'll be easy because I'll be able to take out a GCF. So I'm going to pick the cos 2x formula that, if I add this one over, instead of leaving it here, if I pick the cos 2x formula that has the -1 in it, then the ones will cancel. So we're going to pick that one first. So the 2 sine x cos x stays. And it equals, I'm going to pick 2 cos squared x. I'm not going to pick the 1 minus 2 sine squared x one, because then that would get 1 plus 1, and that would be a 2. I want the 1 to go away. So I'm going to pick the one where that's a -1. So 2 cos squared x minus 1 is what I'm going to replace cos 2x with. Then I still have the +1 at the back. And now those cancel. Now, whenever I have a squared, I have to move everything to one side, whether it's a quadratic, whether it's trig, whatever it may be. So I'm going to move the cos over. So I'm going to get 2 sine x cos x minus 2 cos squared x equals 0. And now, because I don't have that 1 at the back, that constant, I can just GCF it. So I can take out a 2 cos x. So if I take out a 2 cos x, I'm left with sine x minus cos x. Now this one's actually a little tricky, and I picked this one to start with because it is a little more tricky than the other ones. So we can take these and we can set them equal to 0. Now the reason why when you have a basic sine and a basic cos, you can just take it and set it equal to 0 is because sine and cos turn into cotan or tan. So I'll show you that. So I'm going to take these up here and solve them. So 2 cos x equals 0. And then you have sine x minus cos x equals 0. So for this one, I can add the cos over. So I get sine x equals cos x. And then I can divide by sine. And this becomes a 1. So I actually get 1 equals cotan x, which is actually the same as tan x equals 1, because it'd be 1 over 1 flipped. My solutions are between 0 and 2 pi. So where does tan x equal 1? At quadrant 1 and quadrant 3, because that's where tan x is positive, and at the 45. So it's going to be at pi over 4 and 5 pi over 4. Then we can come back to this one over here, divide by 2. So it's where cos x equals 0. Where does x equal 0? X equals 0 at pi over 2 and 3 pi over 2. Up here and here. So x equals pi over 2 and 3 pi over 2. And then you can put your solutions together. So x equals pi over 4, pi over 2, 5 pi over 4, and 3 pi over 2. I just like putting them from the least to greatest, but it doesn't matter. So that would be your solution to that one. All right. For the next one here, you could go square root 2 sine squared x, and then you can write tan as sine x over cos x. times cos x. And these cos x cancel. But before you actually cancel them off, you actually have a variable in the denominator. If you have the variable in the denominator, you have to state non-permissible values. So this cos x is in the denominator. So I have to state cos x can't equal 0. Because if cos x equals 0, I would actually have a problem because the denominator can't equal 0. So I have to state restrictions in this case, and I have to say where x can't be. Because if x was there, your solution would be 0 in the denominator. So where does cos x become 0? Well, cos x is 0 where x is equal to 0. So it's going to be x can't equal pi over 2 and 3 pi over 2. So if I got a solution for pi over 2 or 3 pi over 2, I'd have to count them out. Because if I put pi over 2 in for the x's, it would actually get me a 0 down here in this denominator, which is a problem because I can't have a 0. I can't divide by 0. So even in trig, whenever I have a denominator with a variable in it, I still have to state my non-permissible values. Okay? So now, since I stated my non-permissible values, I can actually cancel. You always state non-permissible values before you cancel anything out of the denominator. And now I'm left with square root 2 sine squared x equals sine x. Remember, whenever I have a squared, whether it's a sine or cos or tan, or if it's an x squared or whatever, I have to move everything to one side, set it equal to 0. So I get square root 2 sine squared x minus sine x equals 0. And then you can replace the signs with m's or x's or whatever you want if that makes better for you. A lot of people do. If you don't need to switch it out, then don't. For this case, because I didn't switch the other one out, I'll switch this one out. So I'll switch the sine x out for m. So square root 2m squared minus m equals 0. So I can take out a GCF of m. And I'm left with square root 2m minus 1 equals 0. Then I have to solve them. So I get m equals 0. And I get square root 2m minus 1 equals 0. Square root 2m equals 1. M equals 1 over square root 2. Remember, 1 over square root 2 is actually just square root 2 over 2. So it's right off the unit circle. And remember, m's are actually signs. So I have to state where sine x equals 0 and where sine x equals square root 2 over 2. So sine x equals 0 when y equals 0. Y equals 0 here and here. Now I have to check if it's inclusive of 0 and 2 pi. So it says here it's equal to 0, but it's not equal to 2 pi. So my only solutions then are going to be x equals 0 and pi. But I can't include 2 pi because it's not equal to it here. And then where it equals square root 2 over 2 is at the 45s. So this is going to be at x equals pi over 4 and 3 pi over 4. So my answers are x equals 0, pi over 4, 3 pi over 4, and pi. And I have to make sure those aren't my restrictions. My restrictions are pi over 2 and 3 pi over 2, so I'm okay. Remember, you can always go y1, y2, restrict your window to 0 and 2 pi and find out where they fall, or do it between 0 and 360, get it in degrees and convert. Same thing here, you could go y1, y2, find out where they intersect between 0 and 360 and convert. Remember, you can always check that way. So let's look at C. C is cos 2x equals cos squared x. Now, cos 2x has 3 formulas. There's the cos squared x minus sine squared x formula. There's the 2 cos squared x minus 1 formula. There's the 1 minus 2 sine squared x. I can tell you right now the one I for sure wouldn't pick is the 1 minus 2 sine squared x because it's not going to make it any prettier. What I am going to do is move the cos squared x over so I can see maybe with what I put in with it what will help me. So if I put in the cos squared x minus sine squared x, if I put that in, I'd have cos squared x minus sine squared x minus cos squared x equals 0. The cos squared x's would cancel, and I'd be left with negative sine squared x, which would be good. If I did the 2 cos squared x minus 1 formula, You could still do it that way and you get the same answer. And either of them would actually work in this case. Not always is it good that both work, but this case they do. So the cos squared x and the cos squared x cancel. And I'm left with negative sine squared x equals 0. Divide by negative 1. Sine squared x equals 0. Square root 0. So it equals plus or minus root 0, which 0 doesn't have a sign. So it's going to be sine x equals 0. Where does sine x equal 0? When y equals 0. When it's y equals 0, here and here. Remember, 2 pi isn't included. So it's going to be x equals 0 and pi. 2 pi is an answer, but we can't include it. Okay, example 5 is our last examples we're going to go through. I might end up having to write C and D lower. So we have sine squared x minus cos squared x equals a half. Okay, so our choice is to swap it out with whatever we want. So think about what you might want to swap out. So we could take a negative 1 out of this side, and we'd be left with negative sine squared x plus cos squared x equals a half. That is a formula on your formula sheet, cos squared x minus sine squared x. So you'd have negative 1 cos 2x equals a half. You could divide the negative 1 over, so you'd get cos 2x equals negative a half. And we don't know how to solve anything with a double angle identity directly like that, because we're not forced to. But we could replace the cos 2x with something else. So you could replace it with 2 cos squared x minus 1. You could replace it with 1 minus 2 sine squared x. It's up to you. I'm going to do 2 cos squared x minus 1. So I'm going to knock out C. I'll redo it later, lower. 2 cos squared x minus 1 equals negative a half. And then I'm going to solve for x. So I get 2 cos squared x minus the 1 off, or add the 1 off, so I'm going to get positive a half. And then I'm going to divide by 2. Dividing by 2 is like multiplying by a half. So I'm going to get cos squared x equals a quarter. And then I'm going to take the square root of it. When I take the square root, I take plus or minus. And I'm going to get cos x equals plus or minus a half. Now cos x is plus or minus a half in the 60s. And our domain is restricted between 0 and 2 pi, not inclusive of 2 pi. So this is going to be pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6 would be your solutions. And these are 30s by accident, so this would actually not be correct. I did 30s instead of 60s. So it would be pi over 3, 2 pi over 3, 4 pi over 3. And I think 5. Yeah, 5 pi over 3. I gave the other way instead. Okay. Now we have 2 sine squared minus 3 cos 2x equals 3. We have to replace the cos 2x because that's going to be our trouble. We have 3 options to replace. So we have cos squared x minus sine squared x. Remember that would replace, the 3 would have to be distributed into those, so I don't know if that'd be helpful. 2 cos squared x minus 1. The 3 would have to be distributed in, and then we'd have a sine squared and a cos squared, so I don't think that would be helpful. Then we have 1 minus 2 sine squared x. At least we'd have all signs then, so I'm going to try that one. So we have 2 sine squared x minus 3 bracket 1 minus 2 sine squared x. You have to remember that the 3 goes to both those terms. So you're going to get 2 sine squared x minus 3 plus 6 sine squared x. And then I'm going to move the 3 over. Minus 3 equals 0. So we have 2 sine squared x plus 6 sine squared x, which is 8 sine squared x. Minus 6 equals 0. And now we can just solve. 8 sine squared x equals 6. Divide by 8. Sine squared x equals 3 over 4. Now this isn't one on your unit circle as of now, but when you square root it, it actually works out nicely. See square root, and you get sine x equals, remember there's a plus or minus sign in front. And remember you can split that square root up, so you can get plus or minus square root 3, doesn't break down, but square root 4 breaks down into a 2. So it's actually all the nice square root 3 over 2's, which is actually at every 60 again. So this time I'll write the right ones. So it's pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Okay? For C, I'll do it here, we have 3 cos 2x plus, I'm going to erase that out so I can see it. 3 cos 2x plus cos x plus 1 equals 0. So I'm going to replace the cos 2x again, but the best one to replace at this time would be the cos squared one, because I have a cos x. So you have to make educated decisions. So it's going to be 3 bracket 2 cos squared x minus 1 plus cos x plus 1 equals 0. Distribute your 3 in. So you're going to get 6 cos squared x minus 3 plus cos x plus 1 equals 0. And then you're going to get 6 cos squared x plus cos x minus 2 equals 0. And then we factor it. Now, if you're the person who likes replacing, replace it. M equals cos x. So you get 6m squared plus m minus 2 equals 0. What multiplies to give you negative 12 and adds to give you 1. So it's going to be 6m squared plus 4m minus 3m minus 2 equals 0. Group. You take out a 2m and you're left with 3m plus 2. You take out a negative 1 and you're left with 3m plus 2. And so your factors are 2m minus 1 and 3m plus 2. And so you get m equals a half when you solve that one out. 1 equals 0. And then you get m equals negative 2/3. And m happens to be cos. So we have cos x equals a half. Those are nice, not the unit circle. And then we have cos x equals negative 2/3. That's not off the unit circle, so we're going to have to use reference angles. So cos x equals a half in the positive quadrants and at the 60s. The positive cos quadrants. So this one's going to be pi over 3, and this one's going to be 5 pi over 3. This one we have to get a reference angle. So reference angle equals cos neg 1 of always the positive, so 2/3. So I'm going to actually get a reference angle of 0.841068 radians. If you want to do it in degrees and convert, go ahead. I'm doing radians. So now cos is negative here and here. Our reference angle is here and here. So we're just going to take that and we're going to subtract it from pi to get this one. So pi minus 0.841068676, and we get to 0.3, and then we're going to take pi and add that decimal. And we're going to get 4.0. It's 3.98. So those are our solutions. Now, sometimes your radian measure isn't going to be in exact values. If it's not off the unit circle, you're not going to. You're going to have rounded decimals, and that's absolutely fine. Your homework for tomorrow, which is going to be doing this and some more proofs, will be in Google Classroom. It'll be in the notes section of this link. So I'll link this to a YouTube video, and then in that same spot in the notes below, it'll give the homework. I might also link an assignment to the homework just in case you don't see the notes part. So it'll be in both. And that'll be your assignment for tomorrow. I guess if you're watching the video tomorrow, it's your assignment for the day I'm missing. So for Halloween, this is your Halloween assignment. It'll be below. I know, so much fun. Yeah, happy Halloween.